Namaste and welcome back to JEE Chemistry with Typical Monk. This is Class 28, Organic Chemistry, Part 3, the Reaction Intermediates. Between the reactant and the product lives a fleeting cast of characters. A carbocation, hungry for electrons, a carbanion, heavy with a lone pair, a free radical, restless with a single unpaired electron, and the elusive carbene. They exist for the briefest instant, yet they decide everything: which product forms, how fast, and by which path. And the golden rule is simple: the more stable the intermediate, the easier the reaction. Today, their structure, their hybridization, and above all their stability orders. One idea at a time. Here is what you will master today. First, the 4 reaction intermediates. Second, their structure and hybridization. Third, the carbocation stability order. Fourth, Carbanion and free radical stability. And fifth, rearrangements and where these intermediates appear. One idea at a time. Let us set the foundation. Reaction intermediates. These are short-lived species formed during the course of a reaction. 4 kinds: the carbocation, the Carbanion, the free radical, and the carbene. Electron count. Their stability depends on how the electron deficiency or the excess is shared out. Master line: stabilize the intermediate and you control the reaction's path and its speed. Now look at the picture. The reaction intermediates. The carbocation, a carbon with only 6 electrons. It is sex2 hybridized, planar with an empty p orbital. The free radical, a carbon with 1 unpaired electron, set2 and nearly planar. The Carbanion, a carbon with a lone pair and a negative charge, set3 and pyramidal. The carbene, a neutral divalent carbon with 6 electrons and a lone pair, the 4th fleeting intermediate. Now their shapes, side by side. The carbocation, Sep2, planar with an empty p orbital, only 6 valence electrons. The Carbanion, Cp3, pyramidal with a lone pair, a full 8 electrons. The free radical, Sp2, nearly planar with 1 unpaired electron, 7 electrons. The carbene, a divalent carbon with 6 electrons, either a singlet, which is S-pent, or a triplet. Now, the heart of the chapter: what makes the carbocation stable? The plus I effect. Alkyl groups push electron density onto the positive carbon. Hyperconjugation. The adjacent carbon-hydrogen bonds delocalize into the empty p orbital. Resonance. The al and benzocations are delocalized, and these are the most stable of all. The order: tertiary, then secondary, then primary, then methyl. Aromatic cations. The tropylium and cyclopropenyl cations are aromatic and so unusually stable. Now look at the picture. The stability staircase. The order: tertiary is the most stable, then secondary, then primary, and methyl is the least. Why? More alkyl groups donate density by the plus I effect and by hyperconjugation. Resonance wins. Allyl and benzyl cations are delocalized and beat even the tertiary. Carbanions reverse. For carbanions, the order flips. Methyl and primary become the most stable. Now, the other 2 intermediates. The Carbanion order, it is the reverse. Methyl, then primary, then secondary, then tertiary. The alkyl groups now destabilize. Stabilized by electron withdrawing groups and resonance stabilize a carbanion. The free radical order, like the cation, tertiary, then secondary, then primary, then methyl. Why? Hyperconjugation and the plus I effect stabilize the electron deficient radical too. Allylic and benzylic radicals are also stabilized by resonance. Now the odd one out, the carbene. The carbene, a neutral divalent carbon with only 6 valence electrons. The singlet, its electrons are paired, it is sp2 and bent, and it forms and reacts stereospecifically. The triplet, it has 2 unpaired electrons, a diradical, and it is usually the more stable ground state. Now match each description to its intermediate. Sp2, planar with an empty p orbital goes to the carbocation, sp3. Pyramidal with a lone pair goes to the carbanion. One unpaired electron goes to the free radical. And tertiary over secondary over primary over methyl goes to the carbocation stability order. 4 pairs, each worth memorizing. Now, how many of these statements are correct? Statement 1. A carbocation is Sebs2 and planar. Correct. Statement 2. The Carbanion stability order is tertiary over secondary over primary. Wrong. It is the reverse. Statement 3. Allyl and benzyl cations are stabilized by resonance. Correct. So the answer 2 are correct. Statements 1 and 3. The trap is the Carbanion order in statement 2. Now the 2 mistakes that quietly cost marks. The truth, carbocation stability runs tertiary over secondary over primary over methyl. The trap, using that same order for carbanions, for them it is reversed. The second truth, allyl and benzyl intermediates are resonance stabilized. The second trap, forgetting that a less stable carbocation rearranges to a more stable one by a hydride or a methyl shift. Now, test yourself. Answer in your head before the reveal. That is how G speed is built. Here we go. Question 1. The hybridization of a carbocation, sp2 and planar. Question 2. The most stable simple carbocation, the tertiary. Question 3. The Carbanion order, reversed. The methyl is the most stable. Question 4. What stabilizes alkations? Resonance. And question 5. A neutral divalent carbon, a carbene. Let us gather it all in one breath. 4 intermediates, the carbocation, the carbanion, the free radical, and the carbene. The shapes, carbocation, sp2 planar, carbanion, sp3 pyramidal, radical sem2 with 1 electron. The order, carbocation and radical run tertiary. Over secondary, over primary, over methyl, the carbanion is reversed. The stabilizers, the plus I effect, hyperconjugation, and resonance stabilize a carbocation. Rearrangement, a less stable carbocation shifts to a more stable one. Next class, the reaction mechanisms, substitution and elimination. Stabilize the fleeting. Every organic mechanism turns on a species that lives for an instant. A carbocation is planar and electron hungry, stabilized by alkyl groups, by hyperconjugation, and best of all by resonance. So tertiary beats secondary, beats primary, beats methyl. The carbanion, heavy with the lone pair, reverses that order. The free radical follows the cation, and the carbon stands apart, neutral and divalent. Learn which intermediate a reaction must pass through, and how stable it is, and you can predict the product before you draw a single arrow. Next class, the mechanisms themselves. Sarah, David, Lisa, and John all began exactly where you are sitting now. One idea at a time. You will crack G. I will see you in the next class.